This is the last lecture, and let's start with this thing that you wanted me to solve. So you have an R and C here, and on the background there's a magnetic field. Okay, and that magnetic field is changing. Okay, the magnetic field has a time dependence, and let's say it's something like alpha times t. Okay, or let's write it more scientific. dB over dt is alpha and it's constant. Okay. At the beginning, capacitor is uncharged. Okay. Find the final charge on the capacitor. No, find the charge with respect to time on the capacitor, Q of t. Do you understand the question? You might think there is no battery and charge is zero. Wouldn't it stay zero forever? No. Why is it changing?
Because there's an induced electric field.
There is an induced electric field that we have discovered in previous questions. Do you remember? So there's a magnetic field coming out, right? And it is increasing. So the flux is increasing outwards. So the response must be inwards, right? So there will be a generated EMF that will point in this direction. Okay, I have to give you also the radius of this. Let's say the radius is r. So the induced EMF is going to be d phi b over dt, which is b times pi r squared. It will be this, so it will be alpha pi r squared. That's the EMF, right? The rest is the usual RC circuit. You just have, how was it? It was Q over C, right? Plus, help me out here, plus R times dQ over dt equals the EMF, equals alpha pi r squared. All right? And if you solve it properly, which we did many times, it's going to be alpha pi r squared times C times 1 minus e to the minus t over RC. That's going to be the Q with respect to time. Do you understand the solution of this problem? So ultimately, the charge on the capacitor will be alpha pi r squared times C.
Can I see above?
Yes?
Did you state that magnetic field was increasing or decreasing?
I sort of did. So alpha is positive.
Because I couldn't see it on this screen.
Yes.
Alpha
Alpha is constant and it's greater than 0. All right. I hope you are happy with this problem. So let's move on. Let's look at another problem. An inductor with inductance L. So let me just draw the problem first. R1, R2, and L, and E. And there's a switch here. Okay. An inductor with inductance L and negligible resistance is connected to a battery. A switch S and two resistors R1, R2 as shown. The battery has EMF of E and negligible internal resistance. S is closed at t equals to 0. Find the currents I1, I2, and I3 with just after S is closed. Just after S is closed, what are these currents? Do you have any? Yes?
I1 equals I2 and I3 is 0.
Yes?
Yes.
I3 is 0 at t equals to 0. I1 is equal to I2, which is equal to E over R1. Everybody agrees with this? Yes? What are I1, I2, I3 after S has been closed a long time?
Well, L is out of the page.
Right? Now L is acting like a wire. Remember, at infinity, after you wait for long enough time, inductors act as wires while capacitors act as circuit breakers. And at the beginning, it's the reverse. Okay? So, at the end of the day, at t equals to infinity, you will have just this E connected to R1 and R2. So you can find the equivalent resistance and find I1. I1 is going to be say it again. Okay, yes, let's do it that way. So, oops, sorry. So let's find I2 and I3 and then sum them up. Let's find I2 and I3. So what is I2? E over R1. What is I3? Do you agree? E over R2. What is I1? Sum of I2 and I3. E over R1 plus E over R2. Very good. Okay? And then the battery is replaced with AC voltage, and we don't do that part. But you could have been asked for the time dependence of I2 and I3. Okay? Which will give you, okay, let's do that. Let's change the question and ask for all these currents with respect to time. Okay? So, how would you solve that question? Yes?
In that case, you mean one after another.
First of all, I2 is always E over R1. Do you agree with that? Yes? And if you look at this side, you know, E supplies the voltage to this circuit over here. So you can just ignore this. No, you can't ignore that part. Okay, I take it back. Can you? You can. You can. You can. You can. You can. Yes, because you are only dealing with this current. Of course, this current will have an extra I2 in it, but otherwise you can think of it as the usual RL circuit with an E, which will give you I3. I3 will be just E over R2 times 1 minus E to the minus T. How was it? R over L or L over R? Was it
By L over R. No.
divided by L over R? So
Tau is L over R, so tau is in the denominator.
like this?
Mm-hmm.
Yes. How could we?
Think like I
Look, just imagine. So do I not have this circuit here? So I can just simply ignore this part because I always supply the same. So it will be it would have been different if there was also some resistor here. That would mess it up. But otherwise, the voltage applied across these points is always E. Okay, so you can just take this loop and draw it like this. Although the current over here is I1 and the current over here is I3, there is no internal resistance, so the current I1 doesn't play a role. Does it make sense? Yes? Yes.
Will we be asked an LRC question?
Could be. But
because in physics 101, damped oscillations were introduced, but I think they were never asked.
Yes, I think we almost never ask it. Okay. So this is I2 and I1 time dependence is simply I2 plus I3. Okay, that's what it is. Good. Yes. Say it again, please. Okay, very good question. It's R2. Right? Because we assume that that's only the... Yes. We sort of decouple R1 in this particular question. Yes.
Can we find evidence of these circuits?
Evidence?
Impedance?
Impedance is not in the exam, but yes, we can.
Can we talk about impedance when we are talking about DC circuits?
You shouldn't. Thank you. Like, DC circuits are like very slowly changing AC, right? So omega goes to 0. Do you see what I mean?
Yes.
So L will act as 0 resistance, which it does, right? And capacitor will act as a circuit breaker, which it does. Like once you go over the transient period, that's exactly how they behave. Do you understand my point? Yes. Thank you. All right. This is an interesting question. Just give me a moment, please. Okay, let's do this one because it's included. Let me just take this one over here. Here's an example. A cylindrical conductor with radius r and resistivity ρ carries a current I. The current is uniformly distributed over the cross-sectional area of the conductor. So it's something like this. We know the resistivity ρ, and it's carrying current I in this direction, let's say, and it's uniformly distributed, and the radius is r. Okay. Find the magnitude of the magnetic field as a function of the distance r from the conductor axis for both inside and outside. If the current is constant in time. If the current is constant in time. So for the part A, I is constant. Let's call it I0, which is constant. And we want magnetic field inside and outside. For inside, you do the Ampere's law. B times 2 pi r equals enclosed current, which is going to be mu 0 times I0 times r squared over small r squared over big R squared. Do you agree with this?
J times A.
J times A. Do you agree with this? So, magnetic field inside is mu 0 I0 R over 2 pi big R. That's inside. Outside,
Capital big R.
then it's simply mu 0 I0 over 2 pi R. There's a mistake somewhere here.
Capital R squared.
Okay. That's part A. You already got your 10 points. Huge. B, part B. What is the electric field inside the conductor? What is the electric field inside the conductor? Okay, 0 if it is for electrostatic. There is a current, so for this one you need to remember the relationship of electric field and current density. Do you remember?
Current density is the change in electric field.
No, current density and resistivity.
Slightly shaken there.
Was it like this or was it 1 over that? Like this, right? Okay. J is current divided by area. You didn't know this? You are surprised? Yes, okay. No meaning that you knew it. Yes. So the electric field is rho times J, which is rho times I, let's call it I0 over pi r squared. Are you happy?
Outside or inside?
Hmm?
Rho neydi? Rho.
Rho is resistivity.
Hocam, aren't we calculating the electric field inside?
Inside.
Then why is it capital R? Hocam, yes. Okay, you're right.
Okay. So something is making this current flow, right? And that thing has to obey this law. Okay, this is basically Ohm's law for this structure. Okay. Finally, find the magnitude of the magnetic field as a function of the distance r, both inside and outside, if the current decreases at a constant rate. So this time things change. This time, part C, I have I equals to I0 minus beta times T. This time, Ampere's law has a Maxwell contribution here. You are very worried. Why you are so worried? Do you remember Maxwell's contribution? Maxwell's term.
This part is not.
This part is chapter 30. That's why I'm solving it, so that you remember that it's chapter 30. Mu 0 times I of the current plus the displacement current. Okay? This time the electric field is changing because the current is changing. Right? The electric field, remember the electric field was rho times current over pi r squared. Okay? Actually, I'm going to write it down. Okay. Why can't I write it like that? I can write it like this. Yes, öyle yazamazsınız dedin de.
Bıraktınız ya ondan da o şekilde.
I0 minus BT, right?
This-
Yes? This is the electric field. Are you following?
No, current changes, then magnetic field changes. Magnetic field changes. Electric field.
That's another effect, but let's concentrate on the fact that there's a current that generates magnetic field, okay? And also, since current is changing, the applied electric field is changing. That is creating the extra amperes extra Maxwell's term as a displacement current. Okay, so the displacement current will be epsilon 0 d phi e over dt, which is epsilon 0 times d phi e over dt will be just d e times pi r squared over dt, right? And
Small r, by the way, right?
no, big R. Okay, small r. Yes, you are right. So this is the displacement current for a certain region. Let me just explain it to you. Sorry. So I take the amperes loop somewhere here at a distance r. For this r, the phi e is e times pi r squared, right? And it's changing with time. So id is epsilon 0 times pi r squared times dE over dt, which is negative of rho beta over pi big R squared. I hope you did follow this. So I get negative rho pi, no, not pi anymore, rho epsilon 0 beta R squared over R squared. Okay? So I can write down Ampere's law with Maxwell's correction. B times 2 pi r is equal to mu 0 times I0 minus beta t. No, not even that. I have to multiply it with r squared over r squared. I hope you are not completely detached from the problem. Are you?
İki yüzlüğü unutmayalım. Onun için.
Hocam ID'yi iki kere mi bulduk biz?
What?
ID'yi iki kere mi bulduk?
No. This is IC. This is ID.
Hocam yukarıda iki tane ID'ye eşitsin diye bir şeyler var.
Do you mean this one?
Mavi ve siyah iki tane var.
Yes, they are the same thing. I just inserted this electric field expression inside here. Okay? Does make sense? So as a result, let me just copy from here and we can check whether this is correct or not. B is equal to
Ortakları çıkaralım.
mu 0 times
Small r.
I0 minus beta t minus rho epsilon 0 beta r over 2 pi big R squared. That's what we get. Okay? How was it? Not good, not terrible? Yes. What else? Outside, it's the same story. Just replace R's with, well, I think they don't even ask R's outside. No, they do ask R's outside, but
Same story.
yeah.
Same story.
Outside, it's the same story. This is for B R less than R. B for R larger than R. It's going to be the same story. Just let me quickly write the same thing,
And small r is equal to capital R.
but this time it's 2 pi R here. No, did I make a mistake?
No. It should be correct.
Everything is fine? Good.
Bir şey göremedim.
Neither did I. Okay. Good. Still have time? Still have time. Let's see what this question is asking. Okay, interesting question. I have a very long line of charge with uniform density lambda, like this, concentric with a cylindrical tube of inner radius R1 and outer radius R2 containing uniform volume charge density rho. So it's concentric with this, and I assume that both of them go to infinity, more or less. Okay, this one has R1 inside, R2 outside. The question starts by saying that the electric field outside the tube is 0. So electric field around here is 0. Find the relationship between lambda and rho. Lambda is the linear charge density of this. Rho is the charge density of the outer shell. Do you understand?
Quad XR dediğimiz şey, quad XR kablo dediğimiz şey.
Coaxial cable means that their axis, what is the plural of axis? Axis, right? No, it's not. It's written like this, I think. Anyways, the axis of one and the axis of the other are the same axis.
Hocam doğrusu
Hmm?
doğrusu.
It was correct, right? So-
What's the difference with this case?
It-
Their axis is
So there is a linear charge in the middle, right? Then there is a tube around it. Tube has void inside, inner radius R1, outer radius R2.
I mean, linear charge and a wire is the same thing, isn't it?
Wire, it's a wire.
So, okay.
Okay, you will figure it out. Don't worry. So how can this?
The void is the R1
Yes.
right? And the R2 is just
Yes.
normal
This part,
solid
oops,
part.
the solid part is between R1 and R2.
Okay. İçi dolu full şey.
Yes, this part is full.
And it is insulating.
It is insulating, yes. So we need to find the relationship between lambda and rho, given that the electric field outside is 0. What do we use?
Gauss's law.
We use Gauss's law. The enclosed current, the enclosed charge must be 0, right? So if I take a Gauss surface over here, right? The enclosed, so let's say it has a length L, then lambda times L must be negative of rho times pi R2 squared minus R1 squared times L. So that's the relationship between lambda and rho. Lambda is equal to minus rho times pi times R2 squared minus R1 squared. Do you see it?
5 points.
5 points for this. Yes. But it's worth it. I would give even 8, 7 because you are using a physical concept here. Find the electric field magnitude for R less than R1 and R between R1 and R2. Express your terms in terms of rho. Do you understand the question?
Gauss's law.
So it's again Gauss's law, but this time we are trying to find the electric field between these, right? So at any distance r, let me just plot it again. So you have lambda inside, this is R1, this is our R. So if you have a length of L, let's say the Gauss's surface has a length of L, then E times 2 pi R times L needs to be enclosed what? Q. So I want to express, so I'm going to eventually express everything in terms of rho, right? So let's keep using rho. So the charge that I have here is rho times pi r squared minus r1 squared. Do you agree with this? But then I also have plus and what? I have L also, right? Plus lambda times L, but lambda itself is negative rho pi r2 squared, blah, blah, blah. So let me just insert it over here. So I have negative of rho. We have to, it doesn't mean that rho is, rho itself could be negative. We don't know which one is negative, which one is positive. Okay?
They can have the same sign.
Biri neden negatif olmak zorunda?
Because the electric field outside is 0. And also this formula tells us that. Doesn't it? So there is a cancellation here. L'ü unutmayalım. Else cancel. Also R1s cancel, right? So E times 2 pi R is, okay, let them live for a little while. Yes, now we can cancel them as well. Rho over 2R times R squared minus R2 squared. Okay, this is for the in-between. And inside, it's much easier. It's lambda over 2 pi R epsilon 0. We forgot epsilon 0. Oh my God. This is for inside. Do I need to explain how I found it? Do I need to explain the last part? Well, the problem tells me that I should use rho. Was that your comment? Yes. So I should really write negative rho pi r2 squared minus r1 squared over 2 pi r epsilon 0. Okay? Okay, thank you very much. Take good care.